Spring 1943. Kummersdorf Proving Ground, Brandenburg, Germany. The captured M4A1 Sherman rolled off the transport railcar, its American star still visible beneath hastily painted identification numbers. Engineers from the Wehrmacht testing facility had already prepared their examination protocols, clipboards ready, measuring instruments arranged on tables beneath canvas awnings. This tank, designated Beutepanzer 147 and nicknamed War Daddy 2 by its American crew, had been captured intact during the Battle of Sidi in Tunisia just weeks earlier. Serial number USA 3067641, built by Lima Locomotive Works, belonging to Company G of the First Armored Regiment. First Armored Division. German intelligence had received reports about American tank capabilities, but this would be the first opportunity for systematic examination under controlled conditions. The Sherman sat before them, representing something German engineers struggled to accept. American industrial capability translated into functional reality. What they would discover in the coming weeks, particularly regarding the tank's hydraulic systems, would force a reckoning with assumptions about American engineering sophistication that propaganda had carefully cultivated for years. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. German test engineers approached the examination methodically, documenting every component with the thoroughness that characterized Wehrmacht technical analysis. They photographed the Sherman from dozens of angles. They measured every dimension with precision instruments. They stenciled armor thickness and angle measurements across the hull and turret in white paint, creating a map of specifications that would guide their penetration tests. The turret particularly demanded attention. German tanks employed various traverse mechanisms, but none with the characteristics displayed by the Sherman's oil gear hydraulic system. The test engineers noted immediately how the turret rotated smoothly through 360 degrees, powered by an electric motor driving a hydraulic pump and turbine assembly compact enough to mount directly within the turret basket. The system demonstrated variable speed control based on gunner input, allowing both rapid traverse for target acquisition and precise micro-adjustments for final aiming. This combination, precision married to power in a single integrated system, represented an approach to hydraulic engineering that German designers had considered but never successfully implemented in production tanks. German engineers disassembled the turret traverse mechanism, laying components on clean canvas sheets, photographing each stage of the process. The oil gear unit revealed manufacturing quality that seemed almost excessive by German standards. Tolerances that allowed smooth operation across temperature ranges from North African heat to European winter cold. Components machined to specifications that prioritized consistent performance over theoretical optimization. The hydraulic motor itself demonstrated design philosophy differences that extended beyond simple mechanical function. American engineers had created a system that remained functional even when turret ring alignment deviated from perfect specification, when minor battle damage introduced friction, when dirt accumulated in mechanisms during field operations. The system included redundancy and margin throughout, accepting slightly lower theoretical efficiency in exchange for dramatically improved operational reliability. This approach contradicted German design principles that emphasized precision engineering and optimal performance under ideal conditions. German turret traverse mechanisms required careful maintenance of tight tolerances. Minor damage or wear could render the system inoperative, requiring skilled technicians with specialized tools to restore function. The Sherman's hydraulic system simply continued working through conditions that would disable German equivalents. Test. Engineers conducted comparative trials, operating the Sherman's turret traverse under various conditions, designed to reveal weaknesses and limitations. They measured traverse speed, documenting that the turret completed a full rotation in 15 seconds, twice as fast as the Panther's hydraulic system could manage. They tested the mechanism at extreme angles of inclination, confirming that the system maintained consistent performance even when the tank operated on steep slopes that would cause German traverse mechanisms to bind or fail. They attempted to overload the system by traversing rapidly back and forth, searching for signs of overheating or mechanical stress. The hydraulic fluid temperature remained within acceptable limits throughout extended operation. The electric motor driving the pump showed no signs of strain. The entire assembly performed exactly as designed, hour after hour, with reliability that seemed almost inexplicable to engineers accustomed to frequent mechanical intervention. The stabilizer system integrated with the turret hydraulics presented another revelation. German engineers had attempted to develop gun stabilization for years without achieving practical results. The complexity of maintaining gun elevation during vehicle movement, the precision required in hydraulic controls, the integration of gyroscopic sensors with mechanical systems, all proved beyond German industrial capability to produce reliably in quantity. The Sherman mounted a functional stabilizer as standard equipment on every tank equipped with the 75mm gun. The system used a gyroscope and hydraulic power drawn from the turret traverse mechanism to maintain gun elevation during movement. German test engineers examined this system with particular interest, recognizing sophisticated engineering that combined multiple technologies into an integrated whole. The gyroscope itself, manufactured to precision standards that ensured consistent performance, mounted in a housing designed for protection from shock and vibration. The hydraulic valves that translated gyroscope signals into corrective adjustments, engineered with responsiveness that prevented oscillation while maintaining positive control. The mechanical linkages connecting hydraulic actuators to gun elevation mechanisms, designed with sufficient strength to control the weapon's mass, while introducing minimal friction or backlash. Every component reflected engineering maturity that came from decades of civilian industrial experience. American automotive industry had pioneered hydraulic systems for brakes, steering assist, and other applications through the 1930s. That accumulated knowledge translated directly into military applications when war production began, providing American designers with proven solutions to problems German engineers still struggled to solve. The powertrain examination revealed additional hydraulic applications that contributed to the Sherman's remarkable automotive reliability. The transmission oil system used both pressure and gravity circulation, with oil pumped to bearings under pressure, then dripping onto gears before collecting in the sump for recirculation through a cooler mounted on the rear firewall of the fighting compartment. This system maintained consistent lubrication across operating conditions that would cause German transmissions to fail. The oil capacity, 152 quarts, shared between transmission, differential, and final drives, provided thermal mass that resisted temperature spikes during sustained operation. The cooler ensured that even during extended movement, oil temperatures remained within acceptable limits, preventing breakdown of lubricant properties that would accelerate wear. German test engineers noted with grudging admiration how American designers had engineered the entire powertrain as an integrated system. The transmission received priority oil flow to maintain lubrication under all conditions. The oil cooler positioning ensured maximum heat dissipation without requiring additional pumps or complex plumbing. The capacity exceeded immediate requirements by substantial margins, providing protection against the inevitable oil consumption and leakage that occurred during field operations. The final drives demonstrated another application of American hydraulic engineering philosophy. Unlike German designs that employed straight-cut gears in housings that proved inadequate for sustained loads, the Sherman used herringbone-cut gears that distributed stress across multiple teeth simultaneously. This design, standard in American heavy equipment manufacturing, provided exceptional durability with relatively loose tolerances. German engineers examining the final drives recognized immediately that American manufacturers possessed capabilities German industry lacked. Producing herringbone gears required specialized cutting equipment and manufacturing expertise that German factories, stretched thin by war production demands, could not replicate at scale. The Americans manufactured these components by the thousands, equipping every Sherman with final drives engineered to exceed the immediate requirements by comfortable margins. The auxiliary hydraulic systems throughout the Sherman revealed additional evidence of American engineering sophistication. The M1 dozer blade kit, designed for field installation, powered itself from the transmission drive shaft through a hydraulic pump mounted to attachment points cast into the transmission housing. This modular approach, designing the base vehicle to accommodate future accessories through standardized mounting points and power takeoffs, demonstrated planning that extended beyond immediate battlefield requirements. German engineers found this growth potential particularly troubling. The Sherman's basic design accommodated upgrades and modifications without requiring fundamental redesign. The large turret ring accepted heavier guns with minimal modification. The transmission and final drives, engineered with substantial margins, handled increased vehicle weight without reinforcement. The electrical system included backup capacity for additional equipment. This flexibility meant the Sherman would remain relevant as American engineers developed improved variants. The German Panther, by contrast, had been designed to precise specifications that left little room for modification. Attempts to increase armor protection or install heavier weapons required extensive redesign that strained already overtaxed industrial capacity. The hydraulic fluid itself presented another American advantage that German engineers noted during their examination. The Sherman used petroleum-based hydraulic fluid that remained functional across a wide temperature range and resisted breakdown under operating conditions. German hydraulic systems employed various fluids depending on application and availability, none optimized for the full range of conditions tanks encountered in field operations. American chemical industry, substantially more advanced than German equivalents, produced specialized fluids engineered for military applications. These fluids maintained consistent viscosity across temperature extremes, resisted oxidation that would degrade performance, included additives that protected metal surfaces from corrosion, and remained stable under the pressures and temperatures generated in hydraulic systems. German test engineers conducting long-duration trials discovered that the Sherman's hydraulic systems required minimal maintenance between major overhauls. The turret traverse mechanism operated for hundreds of hours without adjustment or fluid replacement. The transmission cooling system maintained oil quality through extended operations that would have demanded multiple fluid changes in German vehicles. This maintenance advantage translated directly into operational availability that German forces could not match. American tank battalions could sustain continuous operations without extensive maintenance halts. German panzer divisions had to carefully husband their limited operational vehicles, calculating that every movement consumed precious remaining component life and brought mechanical failure closer. The standardization apparent throughout the Sherman's hydraulic systems impressed German engineers who recognized the manufacturing sophistication required to achieve true interchangeability. Components from different manufacturers fit together without adjustment or modification. Repair parts from one Sherman worked perfectly in another regardless of production date or assembly plant. This level of standardization remained largely theoretical in German tank production. Each manufacturer introduced subtle variations that prevented true parts interchangeability. Field maintenance personnel struggled with components that required individual fitting and adjustment. The complexity multiplied problems as supply lines stretched and deteriorated under Allied bombing. American industry had mastered mass production techniques through decades of civilian automotive manufacturing. That maturity translated into military production that maintained quality while achieving quantities German industry could never match. The hydraulic systems in every Sherman reflected this industrial sophistication, delivering reliable performance through design philosophy that prioritized practical functionality over theoretical perfection. German engineers preparing their evaluation reports faced uncomfortable conclusions about American capabilities. The Sherman's hydraulic systems demonstrated engineering excellence in areas German industry had struggled to master. The integration of multiple hydraulic applications into a coherent whole, the quality of individual components, the manufacturing precision that enabled true interchangeability, all exceeded what German designers had achieved despite their theoretical knowledge and scientific expertise. The reports circulated through Wehrmacht technical branches, providing senior officers and armaments ministry officials with sobering assessments of American industrial advantages. These internal documents, classified to prevent damaging morale, painted a picture of technical capability that contradicted propaganda narratives about American industrial crudeness and lack of sophistication. By summer 1943, additional captured Shermans arrived at Kummersdorf, providing opportunities for comparative analysis across different variants and production periods. Engineers examined the M4A2, with twin General Motors 6046 diesel engines, noting its hydraulic systems matched the specifications established in the initial examination of War Daddy 2. They evaluated the M4A3 with the Ford GAA V8 gasoline engine, finding consistent hydraulic system design across powerplant variations. This consistency across variants demonstrated American commitment to standardization that simplified logistics, training, and field maintenance. German tank production, by contrast, featured multiple variants with incompatible components that complicated supply chains and multiplied training requirements. The Americans had solved fundamental problems in production engineering that German industry never mastered during wartime conditions. The Panther and Tiger tanks rushed into production to counter Soviet armor and maintain tactical advantages, suffered from hydraulic system problems that German engineers recognized would require years to resolve through iterative improvement. The Panther's turret traverse, powered by hydraulic motor driven from the main engine through a secondary drive shaft, proved sensitive to engine speed variations and turret ring imperfections. The system worked adequately under optimal conditions but failed frequently in field operations, when battle damage, wear, or contamination introduced friction or misalignment. Tiger hydraulics, more sophisticated and theoretically superior, demanded constant expert maintenance that became increasingly scarce as trained personnel were killed or captured. The complexity that impressed during peacetime development became a liability during wartime operations, when simplicity and reliability determined whether vehicles remained functional. The Sherman's hydraulic philosophy, accepting slightly reduced theoretical efficiency in exchange for dramatically improved reliability and ease of maintenance, proved far more effective under actual combat conditions. German commanders, receiving Shermans through capture, discovered immediately that American tanks continued operating through circumstances that would disable German vehicles, requiring substantially less maintenance intervention to remain combat effective. Kummersdorf test protocols included endurance trials designed to stress every system under controlled conditions. Engineers drove the captured Shermans through obstacle courses, measured performance across varying terrain and slopes, monitored temperatures and pressures throughout extended operations. After each trial session, they disassembled components to examine wear patterns, searching for signs of stress or design weaknesses that could be exploited tactically. The hydraulic systems consistently performed exactly as designed, showing minimal wear even after hundreds of hours of deliberate abuse. The turret traverse mechanism maintained smooth operation without adjustment. The transmission cooling system kept fluid temperatures within acceptable limits. The final drives operated without signs of stress or impending failure. These results contradicted everything German tank doctrine had accepted about necessary trade-offs between performance and reliability. The Sherman achieved adequate performance in every category while excelling in operational endurance without maintenance intervention, the single metric that determined whether armored units could execute assigned missions. By autumn 1943, Kummersdorf had accumulated sufficient data to produce comprehensive internal reports that documented American hydraulic engineering advantages in devastating detail. These technical assessments, distributed to senior Wehrmacht officers and armaments ministry officials, made clear that German industry fundamentally lacked the manufacturing sophistication and production expertise to replicate American hydraulic system designs during wartime conditions. The knowledge that American tanks incorporated hydraulic technologies German engineers understood theoretically but could not manufacture practically represented more than tactical intelligence. It revealed industrial maturity gaps that extended beyond individual weapon systems to fundamental questions about relative national capabilities in mass production, quality control, and engineering integration. German designers working on next-generation tank projects attempted to incorporate lessons learned from examining captured Shermans. But knowledge of superior design philosophy and understanding of manufacturing requirements provided limited benefit when German industry lacked the equipment, skilled workforce, and production capacity to implement improvements while simultaneously maintaining existing production rates. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. American factories, safely located beyond any combat zone and staffed by motivated workers earning good wages under decent conditions, produced Shermans incorporating sophisticated hydraulic systems by the tens of thousands. German factories, dispersed to avoid bombing and increasingly reliant on forced labor, struggled to maintain quality control on existing designs, while Allied bombing systematically destroyed critical bottlenecks in the production chain. The fundamental difference between American and German tank hydraulics lay not in theoretical engineering knowledge, but in industrial capability and underlying design philosophy. German engineers understood hydraulic principles as well as their American counterparts, possessing extensive scientific expertise. They simply never applied that knowledge consistently to create practical systems that could be manufactured reliably at scale and maintained effectively under field conditions. The Sherman represented decades of American civilian hydraulic experience translated into military applications. Automotive industry experience with power steering, hydraulic brakes, and other civilian technologies provided proven design solutions that American engineers adapted for tank applications. German industry lacked comparable civilian hydraulic manufacturing base, leaving military designers without the accumulated practical knowledge that American engineers drew upon freely. Spring 1944 brought expanded testing programs, as Wehrmacht forces retreated across multiple fronts and additional captured equipment reached Kummersdorf. Engineers continued systematic examination of Sherman variants, building comprehensive databases of American tank capabilities across different models and production periods. Every examination confirmed initial conclusions about hydraulic system superiority that German industry could not match. The broader implications of Sherman hydraulic advantages extended beyond turret traverse and gun stabilization to encompass the entire philosophy of armored warfare. German doctrine emphasized individual vehicle superiority and impressive specifications that looked formidable on paper. American doctrine prioritized keeping maximum numbers of vehicles operational and combat-ready through reliable mechanical systems that functioned consistently under field conditions. This philosophical difference manifested clearly in hydraulic system design choices. German engineers pursued theoretical optimization, designing systems that achieved maximum performance under ideal conditions but proved fragile when faced with battlefield reality. American engineers designed for sustained operation under worst-case scenarios, accepting slightly reduced peak performance in exchange for systems that continued functioning when battle damage, contamination, temperature extremes, or inadequate maintenance degraded conditions. The Panther's hydraulic turret traverse system exemplified German design philosophy and its fundamental limitations. The Boehringer Sturm L4 hydraulic motor, driven from the main engine through a secondary drive shaft, achieved impressive specifications when new and properly maintained. On early production Panthers, maximum turret traverse speed reached 6 degrees per second. Later versions incorporated a selectable high-speed traverse gear that improved performance, but the system depended entirely on main engine operation for hydraulic power. When the engine stopped, turret traverse ceased immediately. This created tactical vulnerabilities that American crews learned to exploit. A Sherman whose engine had been disabled by mechanical failure or battle damage retained turret traverse capability through the backup generator that could power the hydraulic system independently. German tankers whose engines stopped found themselves unable to track moving targets or respond to threats from changing directions. The Panther system also proved sensitive to turret ring imperfections that inevitably developed during field operations. Minor battle damage that bent the turret ring slightly, accumulated dirt and debris that increased friction, wear that introduced play in mounting surfaces, all degraded traverse performance significantly. The system required constant adjustment and maintenance by skilled technicians to maintain acceptable function. Sherman turret traverse, by contrast, incorporated design margins that accommodated inevitable wear and damage. The oil gear system continued operating smoothly, even when turret ring alignment deviated from perfect specification. This tolerance for imperfection meant Shermans maintained functional turret traverse throughout extended operations that would render Panther traverse mechanisms inoperative or severely degraded. German field reports from units employing captured Shermans provided real-world validation of Kummersdorf testing conclusions. Wehrmacht mechanized units, desperate for reliable vehicles, as their own tank inventory degraded, eagerly used any captured American tanks they could obtain intact. Unlike Soviet T-34 tanks, which Germans modified extensively before operational use, Shermans entered German service without changes. They required no modification because they worked correctly as designed, with no fundamental flaws demanding correction. The 10th SS Panzer Division captured 12 M4A1 Shermans at Herlisheim in January 1945 during Operation Nordwind. These tanks, belonging to the American 43rd Tank Battalion, were captured intact when their crews abandoned them during the German assault. The 12 Shermans formed the 13th Company of the 10th SS Panzer Regiment and served in combat operations for the remainder of the war. German tank crews operating these captured Shermans reported consistently on the reliability advantages they experienced. The hydraulic systems continued functioning under conditions that would disable German equivalents. Turret traverse remained smooth and responsive throughout extended operations. The stabilizer, once crews learned to use it properly, provided genuine tactical advantages in acquiring and engaging targets while moving. Most significantly, the Shermans simply worked without constant mechanical intervention. German crews, accustomed to frequent maintenance stops and mechanical failures that immobilized their vehicles during critical moments, found the Shermans' reliability remarkable. This dependability, more than firepower or armor protection, determined tactical utility. During the final chaotic months of the war, a Sherman arriving at the battlefield with operational systems was infinitely more valuable than a Panther with superior specifications broken down behind the lines, awaiting repair parts that would never arrive. German commanders recognized what Kummersdorf testing had proven years earlier. American tanks could be relied upon to function when needed. This fundamental advantage overshadowed whatever theoretical performance superiorities German tanks might possess on paper. Field reports from panzer regiments noted that Sherman operators could focus entirely on tactical considerations and combat effectiveness. Panther and Tiger crews constantly worried about mechanical reliability, calculating whether their vehicles would reach the battlefield without breakdown or complete missions before mechanical failure immobilized them. This psychological burden affected decision-making and tactical effectiveness in ways difficult to quantify but impossible to ignore. The 150th Panzer Brigade, formed specifically for infiltration operations during the Battle of the Bulge in December 1944, attempted to obtain captured American vehicles to disguise their operations behind enemy lines. German planners specifically wanted Shermans because of their reputation for reliability. The brigade ultimately received only 2 Sherman tanks, with only one proving serviceable enough for operations. The fact that German special operations planners specifically requested Shermans for missions requiring vehicles to function without breakdowns while operating far from any support revealed everything about comparative reliability. Even German commanders acknowledged through their actions that American tanks offered dependability German vehicles simply could not guarantee. By late 1944, the pattern had become undeniable to objective observers examining accumulated data. The Sherman's hydraulic systems provided tactical advantages that extended far beyond individual component performance. The integrated nature of American hydraulic design, with turret traverse, gun stabilization, transmission cooling, and other systems working together as a coherent whole, created overall effectiveness that exceeded the sum of individual parts. German tanks featured hydraulic systems designed in isolation, each optimized for its specific function without consideration for how components interacted or how the complete system performed under field conditions. This fragmented approach resulted in vehicles that might excel in individual performance categories, while failing in overall reliability and operational availability that actually determined combat effectiveness. The transmission cooling system exemplified how American hydraulic engineering created cascading advantages throughout the vehicle. The oil cooler, mounted on the rear firewall and drawing oil from the transmission sump, maintained fluid temperatures within acceptable limits during sustained operations. This prevented oil breakdown that would accelerate wear, maintained proper viscosity for effective lubrication, and extended component life substantially beyond what German transmissions achieved. Panther transmissions, lacking comparable cooling systems, suffered from overheating during extended operations that degraded oil quality and accelerated wear. The notorious third gear failure that plagued Panther production throughout the war resulted partly from inadequate lubrication under high load conditions. German field manuals explicitly warned drivers to avoid using third gear except when absolutely necessary, severely limiting tactical flexibility. This single hydraulic system difference, the inclusion of a proper oil cooler in the Sherman versus its absence in the Panther, contributed directly to the dramatic reliability gap between American and German tanks. The Sherman transmission operated for thousands of kilometers without major maintenance. Panther transmissions required constant attention and frequent repair, with drivers learning elaborate techniques to avoid damaging the fragile gearbox. The broader industrial context made these engineering differences even more significant. American hydraulic component manufacturers, drawing on decades of civilian industry experience, produced consistent quality across hundreds of thousands of units. German manufacturers, increasingly reliant on forced labor and dispersed production to avoid bombing, struggled to maintain quality control, even on existing designs. Allied strategic bombing specifically targeted German hydraulic component production facilities when intelligence identified these as critical bottlenecks. The Maybach engine plant in Friedrichshafen, which also produced hydraulic components, suffered devastating damage from Royal Air Force Bomber Command on the night of April 27 to 28, 1944. The raid involved 322 aircraft and destroyed both engine production and associated hydraulic manufacturing capability. Production of tank powertrains and hydraulic systems halted completely for 6 months. When production finally resumed in November 1944, quality control had degraded significantly. Slave labor, increasingly employed in German factories as German workers were conscripted for military service, introduced deliberate sabotage. Components were assembled without proper clearances. Hydraulic seals were installed incorrectly. Contamination entered hydraulic fluid during manufacturing. These problems never affected Sherman production, safely located in American factories far from any combat zone and staffed by motivated workers, earning good wages under decent conditions. The consistency of Sherman hydraulic system performance across the entire production run reflected stable manufacturing conditions that German industry could not maintain during the war's final years. January 23, 1945 brought the final official admission of German hydraulic and mechanical failure. A meeting of the Panzer Commission produced a report documenting catastrophic failures across all German tank types. The document revealed that prior to the 1945 Eastern Offensive, there were 500 defective final drives in the Panzer IV, 370 in the Panther, and roughly 100 in the Tiger. General Wolfgang Thomel, Chief of Staff of the Inspector General of Panzer Troops, explained the operational impact in devastating terms. In such circumstances, orderly utilization of tanks was simply impossible. The troops lost confidence in their vehicles and in some situations abandoned whole vehicles just because of final drive problems, fearing they would be stranded and captured. German tanks, built to intimidate through impressive technical specifications, failed in the most fundamental requirement of armored vehicles: mechanical reliability sufficient to reach the battlefield and complete missions. The hydraulic and mechanical systems that should have provided precision control and sustained performance instead became sources of constant failure and crew anxiety. Kummersdorf testing facility prepared for evacuation in early 1945 as Soviet forces advanced relentlessly toward Berlin. Engineers frantically packed testing data and shipped documentation to facilities farther west, hoping to preserve technical intelligence for post-war analysis. Some captured tanks, including at least 2 Shermans, were pressed into improvised service with combat units desperately defending approaches to Berlin. These vehicles fought alongside German designs in the final desperate battles, providing one last comparison under actual combat conditions. The Shermans continued operating until destroyed by enemy fire or abandoned when fuel supplies ran out. German tanks, including Panthers and the few remaining Tigers, broke down from mechanical failures at rates that shocked even experienced crews accustomed to poor reliability. The hydraulic systems in these final operational Shermans, subjected to the most extreme conditions imaginable, continued functioning exactly as designed. Turret traverse remained operational. Oil cooling systems maintained transmission temperatures. Final drives continued transmitting power without failure. Every system demonstrated the robust engineering margins that American designers had incorporated throughout, providing reliable performance even when vehicle condition deteriorated and maintenance became impossible. The story of German examination of Sherman hydraulics at Kummersdorf represents one of the great industrial and engineering disparities of World War II. German engineers, working within an industrial system that prioritized theoretical perfection over practical utility, could only marvel at American hydraulic systems that simply worked reliably under conditions that defeated German equipment. The testing confirmed what combat experience had already revealed. American engineers, trained in automotive mass production through decades of civilian industry experience, designed hydraulic systems that could be manufactured by the tens of thousands and maintained by mechanics with basic training using skills learned in civilian life. German engineers, lacking comparable civilian industrial base, designed hydraulic systems that looked impressive in specifications but required constant expert attention and could not be produced in sufficient quantities with acceptable quality. Post-war analysis by American and British intelligence organizations examining German technical documents confirmed what Kummersdorf testing had revealed. German understanding of hydraulic engineering principles matched or exceeded American theoretical knowledge. German inability to translate that knowledge into practical, manufacturable, reliable systems reflected industrial limitations rather than scientific inadequacy. The lessons learned through examining captured Shermans directly influenced post-war German tank design thinking. When the Federal Republic of Germany began developing the Leopard 1 main battle tank in the 1950s, designers consciously emphasized reliability and maintainability over pure performance specifications. They studied American hydraulic engineering principles and deliberately applied them to military vehicle development. The resulting Leopard 1 tank incorporated design philosophies that had made the Sherman successful: robust hydraulic systems with substantial design margins, easy maintenance requiring minimal specialized tools, standardized components enabling rapid field repairs, growth potential allowing future upgrades without complete redesign. The Leopard 1 became one of the most successful tank designs of the Cold War era, serving with numerous armies and remaining in production for decades. The captured Shermans at Kummersdorf, including War Daddy II with its distinctive name still painted on the hull, represented tangible proof that industrial maturity and sound engineering principles based on practical experience mattered more than theoretical technical innovation pursued without regard to manufacturing reality or field conditions. German tank designers pursued advanced specifications because they believed superior technology could overcome material disadvantages and numerical inferiority. They were fundamentally wrong. American tank designers built reliable vehicles because they understood through decades of industry experience that hydraulics, maintenance capability, and sustained operational availability determined victory in modern mechanized warfare. They were absolutely correct, and their approach proved decisive. The hydraulic systems in the Sherman, from the oil gear turret traverse to the transmission oil cooling to the stabilizer integration, exemplified American industrial excellence expressed as mechanical reliability and consistent availability. German engineers at Kummersdorf understood this by spring 1943 based on their exhaustive testing. They wrote detailed reports documenting their findings. They tested the evidence repeatedly with scientific rigor. They reached correct conclusions about American advantages. But understanding a problem and solving it are fundamentally different challenges. German industry lacked the capacity to retool production around reliability principles, while simultaneously fighting a losing war on multiple fronts against enemies with superior resources. American industry had built reliability into its civilian hydraulic systems over decades of commercial development and simply extended those mature principles to military production with remarkable success. War Daddy II, that single Sherman tank captured in Tunisia, and tested exhaustively at Kummersdorf for months, told the entire story through its hydraulic system reliability and consistent performance. Every hour it operated without hydraulic failure was evidence that German tank design had prioritized specifications over reliability. Every test that demonstrated American hydraulic excellence was proof that industrial maturity and practical manufacturing experience mattered more than theoretical performance calculations. Every comparison between Sherman and German tank hydraulic systems proved that Americans had solved problems German engineers didn't realize needed solving. The tank itself was unremarkable in many ways, just one of nearly 50,000 produced. What it represented was devastating to German confidence, proof that Germany had already lost the industrial war, even as fighting continued, and that American productive capacity in hydraulic engineering specifically could not be matched regardless of German technical sophistication or tactical skill. The mathematics were simple and brutally clear when examined objectively. A Sherman with hydraulic systems that reliably worked was infinitely more valuable than a Panther with superior specifications, whose hydraulic traverse failed before engaging the enemy. A tank battalion with 80% of its hydraulic systems operational could execute missions that a battalion with 40% operational systems simply could not attempt. Hydraulic reliability wasn't just a convenience factor or secondary consideration. It was the foundation of operational effectiveness, determining whether armored units could execute their assigned missions. German tanks consistently failed this fundamental test throughout the war. American tanks consistently passed it. Kummersdorf testing had proven this beyond any reasonable doubt by mid-1943. The Sherman tank didn't win World War II through hydraulic system superiority alone, but the hydraulic systems exemplified the industrial superiority expressed as mechanical reliability, consistent availability, and ease of maintenance that allowed American armored forces to sustain continuous operations German panzer divisions could not match. German engineers at Kummersdorf understood this, based on their testing. They documented American hydraulic advantages in exhaustive detail. They reached accurate conclusions about industrial maturity differences. But that knowledge could not bridge the gap between German theoretical understanding and American practical manufacturing capability built over decades of civilian hydraulic industry development. The examination of Sherman hydraulics at Kummersdorf revealed a truth German military leadership resisted acknowledging. American engineering excellence in practical applications exceeded German capabilities in areas that determined sustained military effectiveness. The hydraulic systems represented just one example of this broader industrial disparity, but they provided concrete, measurable evidence that German propaganda about American technical inferiority was fundamentally false. Every smooth rotation of the Sherman's turret traverse contradicted years of carefully constructed narratives. Every hour the transmission oil cooler maintained proper fluid temperatures proved American industrial sophistication. Every test of the integrated stabilizer system demonstrated engineering maturity German designers could only aspire to achieve. The evidence was undeniable, documented in thousands of pages of technical reports that circulated through Wehrmacht channels. Those reports told German tank commanders what they increasingly understood through combat experience. American tanks worked reliably. German tanks did not. This fundamental difference in hydraulic system reliability and overall mechanical dependability shaped tactical outcomes more decisively than armor, thickness, or gun penetration statistics that dominated theoretical analysis. A tank whose hydraulic turret traverse functioned consistently could track targets and respond to threats. A tank whose hydraulic systems had failed became a pillbox, useful only for static defense and vulnerable to flanking attacks. German tankers experienced hydraulic failures with devastating regularity. American tankers rarely worried about whether their hydraulic systems would work when needed. This psychological confidence translated into tactical aggressiveness and willingness to maneuver that German crews, constantly concerned about mechanical reliability, could not match. The Sherman's hydraulic dependability enabled American armor to operate with assumptions about vehicle functionality that German armor could never make safely. This intangible advantage, difficult to quantify in technical specifications, proved decisive in determining which force could maintain offensive pressure and which had to carefully ration its limited combat power. The legacy of German examination of Sherman hydraulics extends beyond World War II to influence post-war understanding of industrial capability and military effectiveness. The testing at Kummersdorf demonstrated conclusively that sophisticated engineering knowledge means nothing without industrial capacity to produce reliable systems at scale and maintain them effectively under field conditions. This lesson shaped Cold War military procurement thinking and continues influencing modern defense acquisition philosophy. The most technically advanced weapon system has no value if it cannot be manufactured in adequate quantities, maintained by personnel with realistic training, and operated reliably under actual combat conditions. These practical considerations, which American industry had mastered through decades of civilian manufacturing experience, determine military effectiveness more than theoretical performance maximums achieved under laboratory conditions. The Sherman's hydraulic systems, examined so thoroughly by German engineers at Kummersdorf, stand as permanent testament to American industrial excellence in practical engineering. They represent the accumulation of decades of civilian hydraulic development, translated into military applications by engineers who understood that reliability and maintainability determine success in sustained operations. German respect for American hydraulic engineering, grudgingly acknowledged in classified technical reports, reflected recognition that industrial maturity cannot be replicated quickly through scientific knowledge alone. The gap between German theoretical understanding and American practical manufacturing capability could not be closed during wartime, and that industrial disparity proved decisive in determining the war's outcome. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.